Hello, welcome. We are the 5G cloud-based Spectrum Observatory team. I am Ian.
I'm Christy.
I'm Anila.
I'm Joe.
And I'm Kevin.
Let's get right into it. The goal of this project was to create a proof of concept for a 5G cloud-based Spectrum Observatory, allowing any person anywhere in the world to have access to the data that is being created and output by the radios that were provided to us by the AFRL.
All right, so starting off, we have a basic overview of the project. And so this is the entire kind of block diagram of the system. It's split into three main parts as noted by those dotted lines. And so the first piece, which is the leftmost piece, those are the individual sensor nodes. Those are the pieces of the project that are sampling the 5G spectrum, taking that data in and uploading it to our central cloud server. Those consist of one or two software-defined radios. In this case, we're using the USRP 2901s. And those are paired with GNU radio to do all the sampling and then output the data. That data is then sent to a custom Python script we wrote that does the uploading of the data, which sends all of that kind of information to the cloud with whatever metadata it needs. So the second piece is this centralized cloud server. This is where all of the individual sensor nodes send their data to kind of combine it all for the end product. This is a Node.js web server that has the kind of relatively simple job of taking in the data, formatting it for web display, and then serving whatever web pages and web data is necessary. And of course, the last piece is the web browser. This is the thing the end user interacts with. The spectrum is displayed there, and that's also where users can do remote control of the radio to send commands back to those SDRs to control them remotely.
So this is our test bench where currently you're seeing the single sensor node with two of the radios connected to one of the radio hosts as well as two of their antennas, and each of these radios is designated for specific channels. And this is the flow graph for the GNU radio system we have set up, where the first two blocks you can see that the GNU radio gets a GET request, which requests the specific parameter of the frequency band that it wants to scan, which sends it to the USRP, and then the sampling rate is also sent, and from there the data is scanned and sent back to, and the GNU radio receives it, which calculates the FFT of it based on this FFT size, and it saves it and sends it to the Python script. And here you can see what our GNU radio or flow graph looks like. We have the main UHD USRP source, which takes in the sample rate from the variable sample rate, as well as the center frequency, which is from the variable MQP GET request, which is coming from the web server, and it goes to stream to vector, FFT, and vector to stream before saving it.
So as described in the system overview, once the data is sampled and sent out from GNU Radio, it then goes to a custom Python script for uploading. This diagram here shows a general overview of what that script is doing. So starting on the left, the DAT file from GNU Radio comes in, and the script separates the radio binary data from any metadata information, such as the sample rate, timestamps, stuff like that. That raw binary data is then sent to the piece of the code that encodes it to UTF-8 characters using base64 encoding. This is just so that it can easily be put in a file and uploaded without having to worry about parsing raw binary or sending raw binary to the internet. The encoded data is then recombined with the metadata and sent into a JSON file. That JSON file is what's uploaded to the server and what the server uses to read through the data. Just because, with the server running Node.js, it's easier for it to be a JavaScript object to parse through. After that, the script then creates the post request that uploads that JSON file to the server. Next, this is the kind of general overview of the entire sensor node. So when you combine the uploader script in GNU Radio, there's this kind of hierarchy there. And so as mentioned, the sensor nodes can have 1 or 2 radios running them. And so when either the user or the system starts it starts up one main daemon process that's kind of the controlling process for the whole thing. That daemon process handles any restart commands or anything from the system, and on startup creates 1 or 2 child processes depending on how many radios there are. This case shows if there were 2 radios, you'd have a separate process for each radio. And then each of those processes has 2 threads running, a GNU radio thread and an uploader script. That way, each radio has its own distinct instance of both GNU radio and the uploader to avoid any sort of, conflicts in terms of using resources. And then these both obviously output to the centralized cloud server. These are the 2 kind of samples of what comes out of that sensor node. Since you have it's mostly autonomous, running with a daemon script, the 2 kind of main things a user would be able to see would be top right here, the log file. This basically just gives information for when processes start, when they upload data, if something goes wrong with the data, what the response from the server is, just to allow for better monitoring of the system. The other is the aforementioned JSON file. We have a sample of what that JSON file looks like there in the bottom corner. You have an array of all the metadata. This in this case has the time the sample was taken, the sampling rate, the frequency at which the sample was taken, and then a custom piece of metadata which shows which radio it is. So when the radios start up, they get assigned a number just for control on the server. And then down below that is the payload. Obviously, in a real file, that would be a lot longer. But as you can see, it's just a bunch of characters because it's encoded.
So seeing the server, you can see that there's different requests and different actions that the server kind of manipulates. As an input, we see that there's a data, which is done in base64 encoding, which goes into the server, is posted into the server using HTTP post protocol. The website is also able to request data from the server depending on what it is. If, for example, it would be like the data that's needed to script the spectrograph. There's also a request and post and get request by the user, as if you're changing different frequency lengths or different frequency bandwidths, you'd kind of want to you change it, and then that is sent from the website straight to the server, and the server sends that data back to GNU radio. Again, there's a worker thread that kind of maintains the whole parsing of the data, conversion of the data, and the structure of the data. As as the data is being encoded, as the data has been already encoded in base64 encoding, is to decode all that, parse the data, converts the data, create the CSV file, which is going to be later left, so that in case of a data request from the website, is able to be uploaded and sent to the website. Next.
The figure shows the flow of data from the client side, which is the website, to the host computer. This is done to remotely change the center frequency of the SDRs during runtime. User input on the client side is collected using HTML forms, and then by utilizing HTTP GET POST, this backward flow of data is implemented. As you can see on the upper right corner, that is what the output of the HTML form looks like. On the client side, using radio buttons, the client can choose between 2 predetermined frequencies for each radio. The post request was used to send the user input to the server, where the server stores it for the host computer. HTTP GET was used in the Python script to fetch the frequency value from the server and change the center frequency of the radios. Now, when GNU Radio Companion executed the spectrum sensing flow graph, a Python script called top block was generated. A function, you can see that the function MQP HTTP parser was created to write a while loop for parsing data from HTTP GET. Inside the while loop, a variable freq1 was set to hold the value of the GET request. The URL of the GET request was replaced by the address where the server stored the value of the center frequency. At this point, the thread waited for 5 seconds to create a delay, and then it would send another GET request to the server.
Here we can see the website that we've been designing for the past year. You can see the frequency selection switch here. You can choose either 600 megahertz or 850 megahertz. Hit submit, and it'll submit that frequency to the server and send that back to the radio in order to change the frequency that the website is operating at and displaying. Over on the left here, we have this currently configured to only show one spectrogram at a time, just due to some of the errors that we've come across and some of the things that slow down the website itself. As we click it, you can see the spectrum line getting drawn, and of note, of interest, is the line slowing down as time goes on. This is still trying to display only a single second worth of data, about 290 files total, but you can see that it starts to take more and more time between each line being a single file in the server. All said and done, it can take almost 10 minutes to display even a single second worth of data, which makes this not a very viable option, but is a good proof of concept for what future teams could do in the future. Here we can see some of the main results from the actual website and from the creation of the entire system. Of importance is the increase in total time taken for it to display, or for the website to display, the data that is being collected on the sensor nodes. The cumulative time that you can see on the left is how long it takes the website to actually display a single second worth of data. As you can see, it starts taking upwards of almost 100 seconds or 1,000 seconds towards the end of the actual file, or the actual second worth of data, making this not very usable as a final product. However, it does mean that this would work well as, or that this works as a proof of concept towards allowing future teams to implement further research and start creating faster and faster nodes, networks, and websites.
For the future works, kind of having a different way of going about it will be changing up the different SDRs that are used, which can also help and manipulate the data detection range that each bandwidth is going to cover. Also, an improvement on the data stream and GNU radio to the server that makes it so that the GNU radio just instantly streams the data from the GNU radio to the server, and also can get instructions back from the web server to the GNU radio. Also, having the whole observatory cloud-based, having no host daemons or any computers that can house the USUB, so the USUB will be able to send the data automatically straight into the server. That is something that can be explored, especially also a smoother interface between the back end and front ends of referencing the data, which could also take time. Could also be smoother and more researched, but yes. Thank you very much for everything.
Concludes our presentation. Thank you very much for watching.